Have you ever looked up at the night sky? I mean, really looked up. Far away from the city lights, where the Milky Way spills across the darkness like a splash of cosmic paint. You see countless stars. Each one is a sun, just like our own. Many of those suns have planets orbiting them, and some of those planets might be like Earth. This thought inevitably leads to one of the biggest questions humanity has ever asked. Are we alone in the universe? It is a question that has captivated thinkers, dreamers, scientists, and storytellers for centuries. It's a fundamental inquiry into our own existence and our place in the grand cosmic scheme of things. The question matters for profound reasons. Finding life, especially intelligent life elsewhere, would reshape our understanding of biology, chemistry, and physics. It would tell us that life is not a unique fluke confined to our small blue world. It would suggest that life is a fundamental property of the universe, something that happens whenever the conditions are right. This discovery would be the single greatest in human history. So, how do we go from stargazing to actual science? How do we take this giant philosophical question and turn it into something we can study? In 1961, an astronomer named Frank Drake did just that. He was getting ready for a meeting with other brilliant minds to discuss the search for extraterrestrial intelligence, or SETI. To help guide the conversation, he scribbled an equation on a chalkboard. This equation didn't solve the mystery. Instead, it gave us a framework for thinking about it. It broke the big question down into smaller, more manageable pieces. We call it the Drake equation. Think of the Drake equation as a recipe. It's not a recipe for a cake, but a recipe for finding intelligent, communicating civilizations in our galaxy. It doesn't give you a final, concrete number. Instead, it lists the ingredients you would need to estimate that number. It says, if you want to know how many chatty aliens are out there, you need to figure out these 7 things first. Each term in the equation represents a different factor, a different piece of the cosmic puzzle. It's a probabilistic argument, a way to organize our ignorance and guide our search in a logical way. The equation looks complicated at first glance, like a string of letters and symbols. But the idea behind it is beautifully simple. It starts with the total number of stars in our galaxy, and then progressively filters that number down. Let's unpack this cosmic recipe, ingredient by ingredient. The Drake equation multiplies 7 factors together. The first one is R, the rate of star formation. How many new stars are born in our Milky Way galaxy each year? This is one of the few factors we have a pretty good handle on. We can observe our galaxy and others. We see the stellar nurseries where gas and dust collapse to form new suns. The current estimate is that about 1 to 3 new stars ignite in our galaxy every year. It's a good, solid starting point for our calculation. Next up is F_P, the fraction of those stars that have planets. For a long time, this was pure speculation. But now, thanks to missions like the Kepler Space Telescope, we know that planets are not rare at all. In fact, they are incredibly common. It seems that most stars have planets. Our galaxy is teeming with them, numbering in the hundreds of billions, perhaps even trillions. Finding a star without any planets might actually be the unusual thing. Then we have N_E, the average number of planets that can potentially support life per star that has planets. We call these Goldilocks planets. They are not too hot and not too cold, but just right for liquid water to exist on their surface. Water is the solvent for life as we know it, so this is a crucial factor. We are getting better at spotting these worlds in habitable zones, and our estimates for this number are growing. It might be that billions of such planets exist in the Milky Way alone. This is where things start getting really interesting and also a lot more speculative. The last 4 factors are where we enter the realm of biology and sociology, and our uncertainty skyrockets. There's F_L, the fraction of habitable planets where life actually arises. Then F_I, the fraction of those planets with life where intelligent life evolves. Next is F_C, the fraction of civilizations that develop a technology that releases detectable signs of their existence into space. Finally, there is L, the length of time for which such civilizations release detectable signals. These last 4 ingredients are the great unknowns, taking us from astronomy into very speculative territory. Here is where the Drake equation becomes less of a precise calculation and more of a mirror reflecting our own ignorance. The first few terms, star formation, planets per star, habitable planets, are rooted in astronomy. We can point our telescopes at the sky and collect data. We've made incredible progress. We have narrowed down the numbers from pure guesses to educated estimates. We know that the basic ingredients for life, planets in stable orbits around long-lived stars are common. The universe seems to be very generous in providing potential homes for life. But then we hit a wall. A big one. The factor F_L, the fraction of habitable planets where life actually arises, is a complete mystery. We only have one data point, Earth. Here, life appeared relatively quickly after the planet cooled down enough to support it. This might suggest that the transition from non-living chemistry to biology is easy, even inevitable, given the right conditions. But we can't be sure. It's possible that Earth was an extraordinary fluke. Life might be an incredibly rare chemical accident. We have no way of knowing until we find a second example. The next two factors, F_I and F_C, take us even deeper into speculation. What fraction of life becomes intelligent? On Earth, life has existed for nearly 4 billion years, but only one species, ours, has developed what we call high intelligence and technology. This could mean that intelligence is a very difficult and unlikely evolutionary outcome. The final variable, L, is perhaps the most sobering of all. It represents the lifetime of a communicating technological civilization. How long do they last? We have been broadcasting radio signals for only about a century. Will we last for another 1,000 years? 10,000? A million? Or do all intelligent civilizations inevitably destroy themselves through war, environmental collapse, or some other self-inflicted catastrophe? If L is a very short number, say a few hundred years, then even if many civilizations have existed, the chance of one being active at the same time as us is vanishingly small. This brings us to a deep and honestly, kind of troubling puzzle. When you plug even moderately optimistic numbers into the Drake equation, you can get a result that suggests our Milky Way galaxy should be filled with civilizations. Frank Drake's original conservative estimate suggested there might be thousands or even tens of thousands of them out there right now. If that's the case, and our galaxy is 13 billion years old, then civilizations should have had plenty of time to arise, evolve, and spread out. The galaxy should be buzzing with activity. And yet, when we look and listen, we find nothing. This contradiction is called the Fermi paradox. It was famously posed by the physicist Enrico Fermi during a lunch conversation in 1950. He was talking about the high probability of alien life, and he suddenly asked a simple but powerful question. But where is everybody? If the galaxy is home to many advanced technological civilizations, why haven't we seen any evidence of them? No probes, no giant spacefaring structures, no radio signals, no alien artifacts. The sky is silent. This is really the heart of the paradox, a conflict between the high expectation of life and the stark lack of evidence. The paradox hits hard because of the vast timescales involved. Our galaxy is about 100,000 light-years across. Even with technology not much more advanced than our own, a civilization could colonize the entire galaxy in a few million years. That may sound like a long time to us, but it's a cosmic blink of an eye compared to the age of the galaxy. So the first civilization to arise should have been able to spread everywhere by now. Their presence should be obvious. They should be on our cosmic doorstep, or at least have left some unmistakable sign that they were here. So we are left with this profound silence. Is our science wrong? Are our assumptions flawed? Or is there something deeper and more disturbing going on? The Fermi paradox forces us to confront some uncomfortable possibilities. One of the most discussed solutions to the Fermi paradox is the idea of a great filter. This theory proposes that there is some obstacle, some incredibly difficult step in the evolution of life that makes it nearly impossible for life to reach our current level of technological advancement. This filter could be one of many things. It is a barrier that is so hard to overcome that it effectively weeds out almost all potential life forms before they can become a spacefaring civilization that we could detect. The question is not just what the filter is, but where it is in the timeline of life. One possibility is that the great filter is behind us. This is the optimistic view. Perhaps the filter is the initial spark of life itself, the jump from non-living matter to the first simple cells. Maybe this step is so fantastically improbable that it has only happened once in the entire galaxy, right here on Earth. Or perhaps the filter was the leap from simple prokaryotic cells to complex eukaryotic cells, a transition that took over 1 billion years on our planet. If we are past the great filter, it means we are the first and only ones to have made it through. The more chilling possibility is that the great filter is still ahead of us. In this scenario, life and even intelligence might be common throughout the universe. But there is a barrier that prevents intelligent life from surviving long enough to colonize the galaxy. This could be a technological challenge we have yet to face, or a self-destructive tendency inherent in all intelligent species. Perhaps every advanced civilization discovers a technology that leads to its own annihilation, like nuclear war, runaway climate change, or a mismanaged artificial superintelligence. If this is true, our future is bleak. The discovery of any life, even simple microbial life, on another planet like Mars or Europa, would have profound implications for this theory. If we find simple life, it would suggest that the first step, the origin of life, is not the great filter. This would be exciting, but it would also strengthen the argument that the filter lies in our future. It would mean that many planets start down the path of life, but something prevents them from reaching our stage. The silence we hear from the stars would become a warning. It would be the sound of failed civilizations. Another major category of solutions to the Fermi paradox is more straightforward. The aliens are out there, but for various reasons, we just haven't found them yet. The universe is a vast place, and our search has been, in cosmic terms, incredibly brief and limited. We have only been actively listening for extraterrestrial signals for a few decades. That's like scooping a single cup of water from all the Earth's oceans and concluding there are no whales because you didn't find one in your cup. The galaxy is immense, and we have barely begun to search it. Our methods of searching might also be fundamentally flawed. We are listening primarily for radio signals because that's the technology we understand. What if advanced civilizations have moved on to a different, more efficient form of communication that we can't even imagine? Perhaps they use modulated neutrinos, gravitational waves, or some other physics we have yet to discover. We might be like an isolated tribe trying to communicate with a modern city using only smoke signals. Furthermore, intelligent life might not be interested in broadcasting its existence to the cosmos. Why would they? Announcing your presence in a potentially dangerous universe might not be a wise survival strategy. It could attract unwanted attention from more advanced and possibly hostile civilizations. Perhaps the smart thing to do is to stay quiet and listen. If every civilization adopts this cautious approach, the galaxy could be full of intelligent life, with everyone listening and no one transmitting. The cosmic silence wouldn't be a sign of absence, but a sign of prudence. Finally, there's the simple matter of timing. A civilization's window of broadcasting powerful, leaky signals like our early radio and TV might be very short. As technology becomes more efficient, we are moving towards focused, low-power transmissions like fiber optics and targeted laser communications. These are much harder to detect from interstellar distances. It's possible that the loud phase of a civilization is only a century or two long. If that's the case, we would have to be looking at the right star system at exactly the right, fleeting moment in its history to hear anything. A third, more exotic solution to the Fermi paradox is known as the zoo hypothesis. This idea suggests that advanced alien civilizations are out there and they know we are here. However, they have deliberately chosen not to make contact with us. They are observing us from a distance, much like we observe animals in a nature preserve or a zoo. They have established a hands-off policy, allowing our civilization to develop naturally without interference. The entire Earth, or perhaps our whole solar system, could be a designated wilderness area. This hypothesis assumes a level of technological and sociological maturity on the part of the aliens that is far beyond our own. They would have the capability to travel or send probes across the galaxy, and the technology to remain completely undetected by our instruments. It also implies a shared galactic ethic or treaty among many different civilizations to leave primitive cultures like ours alone. This might be done for scientific study, or perhaps out of an ethical principle similar to Star Trek's Prime Directive, which forbids interference with less developed worlds. The idea is both tantalizing and unfalsifiable. How could we ever prove or disprove it? Any lack of evidence for aliens can be explained away by saying they are simply very good at hiding. It places humanity in a somewhat passive and humbling position, as subjects of study rather than peers in a galactic conversation. We are not alone, but we are isolated in a cosmic enclosure for our own good or for their scientific curiosity. The silence we perceive is not an absence of life, but a deliberately imposed quarantine. There are many variations of this idea. Perhaps they are waiting for us to reach a certain technological or ethical milestone before they reveal themselves. Maybe they will make contact once we have solved our own problems, like war and poverty, or once we have developed the capacity for interstellar travel ourselves. In this view, the Fermi paradox is not a paradox at all. It is simply a reflection of our current immaturity. The everybody that Fermi asked about is waiting patiently for us to grow up and join the Galactic Club. So, where does all this leave us today on August 11th, 2025? The truth is, we are still firmly in the dark. We have theories, equations, and paradoxes, but we have no data. We have one data point, us, and that is not enough to draw any firm conclusions. Recent research has simultaneously bolstered both sides of the argument. The discovery of thousands of exoplanets, many in the habitable zone, makes it seem more likely than ever that the raw materials for life are abundant. The universe appears to be a very friendly place for life to begin. However, other studies have highlighted just how special Earth might be. Factors like the presence of a large moon to stabilize our axis, a strong magnetic field to shield us from solar radiation, and the specific chemical composition of our planet might be rare and crucial ingredients. Some scientists argue that while simple life might be common, the long chain of improbable events that led to human intelligence is so unlikely that we may, for all practical purposes, be alone in the galaxy. The debate between a rare Earth and a common Earth rages on. The answer to the question, "Are we alone?" remains one of the greatest unsolved mysteries. We don't know if the galaxy is teeming with life or if we are a singular, lonely miracle. We don't know if the silence is a sign of absence or a sign of prudence. We don't know if a great filter is behind us or looming in our future. All we know is that the question is too important to ignore. It drives us to explore, to innovate, and to understand our universe on the deepest possible level. This is why the search must and will continue. With new instruments like the James Webb Space Telescope analyzing the atmospheres of distant exoplanets, and with ever more powerful radio telescopes scanning the skies, we are entering a new era of exploration. Every new discovery adds another piece to the puzzle. The quest for extraterrestrial life is a quest for knowledge. It is a fundamental expression of our species' innate curiosity. And in searching for others, we inevitably learn more about ourselves, our planet, and our precious place in the cosmos.